Hello, this is Measurements in Experiments. This is going to be movie one, just in case I make another movie named Measurements in Experiments. And what this does is it reviews everything. It reviews scale reading, how to identify stimulant figures. For instance, list the basic SI units and quantities. They describe, convert measurements into scientific notation, distinguish between accuracy and precision, use significant figures in measurements and calculations, as well as a lot more. And it explains it in detail. So let's begin. Physicists and chemists perform experiments to test hypotheses about how changing one variable in a situation affects another variable. An accurate analysis of such experiments requires numerical measurements. Numerical measurements are different from the numbers used in a mathematics class. In mathematics, a number like 7 can stand alone and be used in equations. In science, measurements are more than just a number. For example, a measurement reported as 7 leads to several questions. What physical quantity is being measured? Length, mass, time, or something else. If it is length that is being measured, what units were used for the measurements? Meters, feet, inches, miles, or light years? And is it 7.0 exactly, or is it 7.00, 7.01, etc.? The description of what kind of physical quantity is represented by a certain measurement is called dimension. In the next several chapters, you will encounter 3 basic dimensions: length, mass, and time. Many other measurements can be expressed in terms of these 3 dimensions. For example, physical quantities such as force, velocity, energy, volume, and acceleration can all be described in combinations of length, mass, and time. In later chapters, we will need to add 2 other dimensions to our lists for temperature and for electric current. The description of how much a physical quantity is represented by certain numerical measurement depends on the units which the quantity is measured. For example, small distances are more easily measured in millimeters than in kilometers or light years. The official standard kilogram mass is a platinum iridium cylinder kept in sealed container at the International Bureau of Weights and Measures in Sèvres, France. About as big as a hen's cup. The original kilo was cast in platinum iridium alloy, polished and honed, then locked in the basement of BIPM, Bureau of International des Poids et Measures in Sèvres, kept in an environmentally controlled chamber under 3 bell jars that can only be opened by 3 keys kept by 3 different people. SI is the standard measurement system for science. When scientists do research, they must communicate the results of their experiments with each other and agree on a system of units for their measurements. In 1960, an international committee agreed on a system of standard, such as the standard shown in Figure 7. They also agreed on designations for the fundamental quantities needed for measurements. This system is called the System International of Units, SI. In SI, there are only 7 base units. Each base unit describes a single dimension, such as length, mass, or time. The units of length, mass, and time are the meter, kilogram, and second, respectively. In most measurements, these units will be abbreviated as m, kg, and s, respectively. Here are the SI standards. Excuse my terrible French pronunciation. I really don't know much French. The meter is the first. And what this is going to do is this is going to define where the actual meter came from and then what the current distance is. This is 1/10,000,000th, the distance from the equator to the North Pole. Sounds like an awfully difficult unit. The distance traveled by light in a vacuum in 3.3356,409 times 10 to the negative 9 seconds. Seems like a very scientific way of doing it. Kilogram, or the mass. The mass of 0.001 cubic meters of water. That's about a liter. It's a liter. It's not about a liter. It is a liter. The mass of a specific platinum iridium alloy cylinder. That is a kilogram. And a second. This might be interesting. Sure, it has something to do with cesium now, something. 1/60th times 1/60th times 1/24th average solar days. Sounds right. And then now it is 9,192,631,770 times the period of a radio wave emitted from a cesium-133 atom. Oh, right, that sounds very scientific. These units are defined by the standards described in Table 2 and are produced so that every meter stick, kilogram mass, and clock in the world is calibrated to give consistent results. We will use SI units throughout this book because they are almost universally accepted in science and industry. NIST-F1, an atomic clock at the National Institute of Standards and Technology in Colorado, is one of the most accurate timing devices in the world. NIST-F1 is so accurate that it will not gain or lose a second in nearly 20 million years. As a public service, the Institute broadcasts the time given by NIST-F1 through the Internet radio stations, WWV and WWVB, and satellite signals. I use it actually every once in a while to set my time, my watch. Not every observation can be described using one of these units, but the units can be combined to form derived units. Derived units are formed by combining the seven basic units with multiplication and division. For example, speeds are typically expressed in units of meters per second. In other cases, it may appear that a new unit that is not one of the base units is being introduced, but often these new units merely serve as shorthand ways to refer to combinations of units. For example, forces and weights are typically measured in units of newtons, but a newton is defined as being exactly equivalent to 1 kilogram multiplied by meters per second squared. And there are many, many examples, but it's the 7 basic units that you really have to worry about in chemistry and physics. Derived units such as newtons will be explained throughout this book as they are introduced. Derived units describe quantities such as density that are calculated from measurements in base units, for instance, mass and volume. And volume is derived from length. Cubic meter is the standard for volume. SI uses prefixes to accommodate extremes. Physics is a science that describes a broad range of topics and requires a wide range of measurements, from very large to very small. For example, distance measurements can range from the distances between stars, about 100 with 1, 2, 3, 4, 5 groups of 3, that's 15 zeros, meter, to distances between atoms in a solid, which are very small, and that's in meters. Here's a mosquito, 1 times 10 to the negative 5 kilograms, or 0.01 grams, or 10 milligrams. Very ugly too, and could be, depending upon where you are and what it's carrying, deadly. Here is a table, table 3. I'm being very dramatic by uncovering it slowly. And it is prefixes for powers of 10. And we will use prefixes in this class. You have probably deduced by now, and that this is from a physics book. But even though it says the word physics every once in a while, it could be written for a chemistry book with very minor changes. So here are the powers. Here are the base 10 powers that you are. And then here's the factor. So that's 10 to the negative 9th, 10 to the negative 6th, 10 to the negative 3rd, etc. And then the prefix. Atto, femto, pico, nano, micro, milli, etc. And then here are the abbreviations. For instance, micro is the Greek letter mu. And then the power, so that would be 10, 20, 30, 40, 10, 100, 1,000, a million, etc. There's the factor, the multiplied factor. And then 10 to the 1 would be deca, and then hecto, kilo, mega, giga, etc., tera, peta, and exa. And those are the abbreviations for the prefix. And then this is just another way of looking at it as an extra table that I put in. And you should memorize this. I know it's the M word, it's a terrible word, but it's, learning doesn't take place in a vacuum. If you don't know anything, you can't think about it. Because these numbers can be extremely difficult to read and write, they are often expressed in powers of 10, such as 1 times 10 to the 17th meters, or 1 times 10 to the negative 9th meters. Another approach commonly used is in SI is to combine the units with prefixes that symbolize certain powers of 10, as illustrated in Figure 8. The most common prefixes and their symbols are shown in Table 3. For example, the length of a housefly is 5 times 10 to the negative 3 meters, is equivalent to 5 millimeters, or mm. And the distance of a satellite, 8.25 times 10 to the 5th meters, from Earth can be expressed as 825 kilometers, km. A year, which is about 3.2 times 10 to the 7th seconds, can be expressed as 32 megaseconds. That's 32 capital M-S, mega. Mega is millions. Converting a measurement from its prefix form is easy to do. You can build conversion factors from any equivalent relationship, including those in Table 3. Just put the quantity on one side of the equation in the numerator and the quantity on the other side in the denominator, as shown below, for the case of the conversion of 1 millimeter, which is 1 times 10 to the negative 3 meters. Because these two quantities are equal, the following equations are also true. Even though they don't look, well, we don't say equal, we say equivalent. Thus, any measurement multiplied by either one of these fractions will be multiplied by 1. It's called a factor of 1. The number and the unit will change, but the quantity described by the measurement will stay the same. It's called a factor of 1, where the numerator equals the denominator. And they don't look the same, but they are, we say, equivalent expressions. So the left is equivalent to the right. To convert measurements, use the conversion factor that will cancel with the units you are given to provide the units you need, as shown in the example below. Typically, the units to which you are converting should be placed in the numerator. It is useful to cross out the units that cancel to help keep track of them. So you need some math skills. So you're going to wherever the units you want to cancel are, you want to put those in the opposite, either denominator or numerator. So you can see if you want to convert millimeters, you want to divide by millimeters. Otherwise, you get something completely screwy. So you want to put them in this case, in the denominator. If the units you want to get rid of are in the denominator, then you put it in the opposite. So it's the opposite wherever you're doing it. So now the millimeters obviously will cancel. So, and then you'll be left with meters. You see how the millimeters cancel, and you're left with meters. And the answer is 37.2 times 10 to the 3.72 times 10 to the second meters. All right, let's continue. Both dimension and units must agree. Measurements of physical quantities must be expressed in units that match the dimensions of that quantity. For example, measurements of length cannot be expressed in units of kilogram because units of kilogram describe the dimensions of mass. It is very important to be certain that a measurement is expressed in units that refer to the correct dimension. One good technique for avoiding errors is, in physics or chemistry, is to check the units in an answer to be certain they are appropriate for dimensions of the quantity, physical quantity that is being sought in a problem or calculation. In addition to having the correct dimension, measurements used in calculations should also have the same units. For instance, if you are converting your height to something, you don't want to convert it to pounds. That would make no sense. Or if you're converting your weight, you wouldn't convert your weight to seconds. That's just silly. Now, this is a very interesting, we call it Why It Matters in this particular textbook, the Mars Climate Orbiter mission. The Spirit of Opportunity rovers have explored the surface of Mars with a variety of scientific instruments, including cameras, spectrometers, etc. The Mars Climate Orbiter mission, the $125 million Mars Orbiter mission, failed because of a miscommunication about units of measurements. That's absolutely true. They didn't do their significant figures correctly. The Mars Climate Orbiter was a NASA spacecraft designed to take pictures of the Martian surface, generate daily weather maps, and analyze the Martian atmosphere from an orbit about 80 kilometers or 50 miles above Mars. It was also supposed to relay signals from its companion, the Mars Polar Lander, which was scheduled to land near the edge of the southern polar cap of Mars shortly after the orbiter arrived. The orbiter was launched from Cape Canaveral, Florida on December 11, 1998. Its thrusters were fired several times along the way to direct it along its path. The orbiter reached Mars 9.5 months later, on September 23rd, 1999. And this is absolutely true. I remember when this happened, everybody in my physics and chemistry classes were stunned that this could have happened. with these sophisticated scientists. They were stunned. It was a great learning experience for everyone. And it was a great lesson for children around the world who studied science that this is not just nonsense that you're studying in the beginning of a course about scientific notation and significant figures. This is real. A signal was sent to the orbiter to fire the thrusters a final time in order to push the spacecraft into orbit around the planet. However, the orbiter did not respond to this final signal. NASA soon determined that the orbiter had passed closer to the planet than intended, as close as 60 kilometers. The orbiter most likely overheated because of friction in the Martian atmosphere and then passed beyond the planet into space, fatally damaged. The Mars Climate Orbiter was built by Lockheed Martin in Denver, Colorado, while the mission was run by NASA flight control team at the Jet Propulsion Laboratory in Pasadena, California. So this is real. This was an amazing waste, monumental waste of money, time, effort, and precious resources that you can't get back. So it was a lesson for everyone. So the only good thing was that it showed the students of America and around the world that you gotta pay attention to significant figures, accuracy, precision, scientific notation, calculations, procedures, unit labels, dimensions, everything. Review of the failed mission revealed that engineers at Lockheed Martin sent thrust specifications to the flight control team in English units of pounds of force, while the flight control team assumed that the thrust specifications were in newtons, the SI unit of force. Such a problem normally would be caught by others checking and double-checking specifications, but somehow the error escaped notice until it was too late. Unfortunately, communication with the Mars polar lander was also lost as the lander entered a Martian atmosphere on December 3rd, 1999. So the Americans' unwillingness to convert completely to metric sabotaged the entire mission. Silliness. Mars Climate Orbiter during assembly. Everybody's dressed so it's all a clean room. The failure of these and other space exploration missions reveals the inherent difficulty in sending complex technology into the distant, harsh, and often unknown conditions in space and on other planets. However, NASA has had many more successes than failures. A later Mars mission, the Exploration Rover mission, successfully placed 2 rovers named Spirit and Opportunity on the surface of Mars, where they collected a wide range of data. Among other things, the rovers found convincing evidence that liquid water once flowed on the surface of Mars. Thus, it is possible that Mars supported life sometime in the past. Here is when the thing lifts off, the booster rockets that actually propel it into an orbit around the Earth. So it blasts off from that orbit, literally blasts off from that orbit to travel to Mars. Unbelievable. Figure 9, when determining area by multiplying measurements of length and width, be sure the measurements are expressed in the same units. As an example, consider figure 9a, which shows 2 people measuring a room to determine the room's area. Suppose one person measures the length in meters and the other person measures the width in centimeters. When the numbers are multiplied to find the area, they will be given a difficult to interpret answer in units of centimeter meter, as shown in figure 9b. On the other hand, if both measurements are made using the same units, the calculated area is much easier to interpret because it is expressed in units of meters squared, or square centimeters could be, as shown in figure 9c. Even if the measurements were made in different units, as an example above, one unit can be easily converted to the other unit because centimeters and meters are both units of length. Or it could be feet or yards, because you can convert those, but you can't measure it in pounds. That would make no sense, or kilograms. Here is another shot of that figure 9, A, B, and C. And we'll do what we call in this book a visual strategy. Point out that all measurements could have been given converted to centimeters. So it could be in square centimeters as well as square meters. Okay, so what would be the area in centimeters if you measured it in centimeters? So it'll be a larger number, but it will be equivalent to the smaller number. So it'll be 2.54 times 10 to the 6th centimeters squared. So it looks larger, but it's the same. They're said to be equivalent. This number is greater than the number in square meters. Does it indicate an error? Does it indicate an error? No. The same sized area contains a small number of larger units, large tiles, or a large number of small units, small tiles, just as $21 bills has the same value as 2,000 pennies. It is also necessary to convert one unit to another when working with units from two different systems, such as meters and feet. In order to avoid confusion, it is better to make the conversions to the same units before doing any more arithmetic. Sample problem A. A typical bacterium has a mass of about 2.0 femtograms. Express this measurement in terms of grams and kilograms. And it says there's the given material. The given is mass is 2 femtograms. And the unknown is the mass in grams and the mass in kilograms. So we want to calculate that value. So build conversion factors from the relationships given in Table 3. Two possibilities are shown below. And here is 1 times 10 to the negative 15th grams over 1 femtogram, and 1 femtogram over 1 times 10 to the negative 15 grams. Those are your conversion factors. Only the first one will cancel the units of femtograms to give units of grams. Then take this answer and use a similar process to cancel the units of grams to give units of kilograms. So I divide by femtograms and I go to grams. So I'm going to use the expression that's going to have femtograms in the denominator. 1 times 10 to the negative 15 grams over 1 femtogram will give me 2 times 10 to the negative 15 grams. So then, after I get this answer, then I will divide by grams and go to kilograms. 1 kilogram divided by 10 to the third grams, which gives me 2 times 10 to the negative 18th kilograms. My answer is 2 times 10 to the negative 18 kilograms. The next problem is I'm going to skip problem 1 and 2 and go right to problem 3. A hydrogen atom has a diameter of about 10 nanometers. So you want to This is for all the problems in number 3. I think there's A, B, and C. So you want to do the first one, you want to go to meters. So we want to cancel nanometers and go to meters. So we need nanometers in the denominator. So it'll be the first one, top left. And that will convert it to meters. And then we have millimeters and meters, and then micrometers and meters. So that's the first one. And so that would be 1 times 10 to the negative 8th meters. So we're going from nanometers to meters. And then express it, the diameter, in meters. So we can either go directly to millimeters, or we can go from meters, because we have 1 times 10 to the negative 8th meters now. We'll go from that to millimeters. And that'll be 1 times 10 to the negative 5th millimeters. And then do it in micrometers. So 1 times 10 to the negative 8th meters multiplied by micrometers over meters, and that'll give 1 times 10 to the negative 2 micrometers. The distance between the sun and the earth is about 1.5 times 10 to the 11th meters. Express this distance with an SI prefix of terameters and in kilometers. So we want to divide by meters and multiply by terameters. There's 10 to the 12th meters in a terameter, and so that gives me 1.5 times 10 to the negative 1 terameters, because 10 to the 11th divided by 10 to the 12th is 10 to the negative 1. Remember your exponent rules from mathematics. And then if you're going to express it in kilometers, it would be 1 times 10 to the 8th kilometers. Because theories are based on observation and experiment, careful measurements are very important in physics as well as chemistry. But no measurement is perfect. In describing the imperfection, one must consider both the measurement's accuracy and the measurement's precision. Accuracy is defined as a description of how close a measurement is to the correct or accepted value of the quantity measured. And precision, the degree of exactness of a measurement. How exact, how reproducible is the measurement? If I took the same measurement 5 times, would they align with one another? Although these terms are often used interchangeably in everyday speech, they have specific meanings in a scientific discussion. A numeric measure of confidence in a measurement or result is known as uncertainty. A lower uncertainty indicates greater confidence. Uncertainties are usually expressed by using statistical methods. Error in measurements must be minimized. Experimental work is never free of error, but it is important to minimize error in order to obtain accurate results. An error can occur. For example, if a mistake is made in reading an instrument or recording the results, one way to minimize error from human oversight or carelessness is to take repeated measurements to be certain they are consistent. Figure 10, if you measure this window by keeping your line of sight directly over the measurement as in A, you will find that it is 165.2 centimeters long. If you do not keep your eye directly over the mark, as in B and C, you may report a measurement with significant error. If some measurements are taken using one method and some are taken using a different method, a type of error called method error will result. Method error can be greatly reduced by standardizing the method of taking measurements. For example, when measuring a length with a meter stick, choose a line of sight directly over what is being measured, as shown in figure 10a. If you are too far to one side, you are likely to overestimate or underestimate the measurement, as shown in figure 10b and 10c. Another type of error is instrument error. If a meter stick or balance is not in good working order, this will introduce error into any measurements made with the device. For this reason, it is important to be careful with lab equipment. Rough handling can damage balances. It's also called systematic error because there's something wrong with the system set up in order to do the experiment, and the balances are part of that system. If a wooden meter stick gets wet, it can warp, making accurate measurements difficult. Because the ends of the meter stick can be easily damaged or worn, it is best to minimize instrument error by taking measurements with a portion of the scale that is in the middle of the meter stick instead of measuring from the 0 centimeter mark. Try measuring from the 10 centimeter mark. Precision describes the limitations of the measuring instrument. Poor accuracy involves errors that can often be corrected. On the other hand, precision describes how exact a measurement can possibly be. For example, a measurement of 1.325 meters is more precise than a measurement of 1.3 meters. Even figure 11, even though this ruler is marked in only centimeters and half centimeters, if you estimate, you can use it to report measurements to a precision of millimeters. And it has to be. I don't know what the book is thinking by saying or giving you the idea that it's, only a possibility. You have to measure. This is a vernier caliper, and these help you to measure that estimated place value. They're to help you, but they still measure to one estimated place value. A lack of precision is typically due to limitations of the measuring instrument and is not the result of human error or lack of calibration. For example, if a meter stick is divided only into centimeters, it will be difficult to measure something only a few millimeters thick with it. In many situations, you can improve the precision of a measurement. This can only be done by making a reasonable estimation of where the mark on the instrument would have been. Suppose that in a laboratory experiment you are asked to measure the length of a pencil with a meter stick marked in centimeters, as shown in figure 11. The end of the pencil lies somewhere between the 18 centimeter and the 18.5 centimeter. The length you have actually measured is slightly more than 18 centimeters. You can make a reasonable estimation of how far between the two marks the end of the pencil is and add a digit to the end of the actual measurement. In this case, the end of the pencil seems to be less than halfway between the two marks, so you would report the measurement as 18.2 centimeters. Significant figures help keep track of imprecision. It is important to record the precision of your measurements so that other people can understand and interpret your results. A common convention used in science to indicate precision is known as significant figures. Those digits in a measurement that are known with certainty, plus the first digit that is uncertain. In the case of the measurement of the pencil as about 18.2 centimeters, the measurement has three significant figures. The significant figures of the measurement include all the digits that are actually measured, 18 centimeters, plus one estimated digit. Note that the number of significant figures is determined by the precision of the markings on the measuring scale. The last digit is reported as 0.2 for the estimated 0.2 centimeters past the 18 centimeter mark. Because this digit is an estimate, the true value for the measurement is actually somewhere between 18.15 centimeters and 18.25 centimeters. When the last digit in a recorded measurement is a 0, it is difficult to tell whether the 0 is there as a placeholder or as a significant digit. For example, if the length is recorded as 230 millimeters, it is impossible to tell whether this number has 2 or 3 significant figures, significant digits. In other words, it can be difficult to know whether the measurement of 230 millimeters means the measurement is known to be between 225 millimeters and 235 millimeters, or is known more precisely to be between 229.5 millimeters and 230.5 millimeters. One way to solve such problems is to report all values using scientific notation. In scientific notation, the measurement is recorded to a power of 10, and all of the figures given are significant. For example, if the length of 230 centimeters has 2 significant figures, it would be recorded in scientific notation as 2.3 times 10 to the 2 centimeters. If it has 3 significant figures, it would be recorded as 2.30 times 10 to the 2 centimeters. Scientific notation is also helpful when the 0 in a recorded measurement appears in front of the measured digits. For example, a measurement such as 0.00015 centimeters should be expressed in scientific notation as 1.5 times 10 to the negative 4th centimeters if it has 2 significant figures. The 3 zeros between the decimal point and the digit 1 are not counted as significant figures because they are represented only to locate the decimal point and to indicate the order of magnitude. Figure 12. If a mountain's height is known with uncertainty of 5 meters, the addition of 0.2 meters of rocks will not appreciably change the height. Here is table 4, and it talks about rules for determining whether zeros are significant figures. Zeros between other non-zero digits are significant. That's easy. So the 0.3 has 3 significant figures. That's correct. Or zeros between 2 significant figures are also significant. So that has 5 significant figures. All right, excellent rule. Excellent. Easy. Zeros in front of a non-zero digit are not significant. So that's non-zero. That's in front of non-zero digits. So that has 3 significant digits. And there's 4 more, and that's only 1 significant figure. So those are easy to understand. Zeros that are at the end of a number and are also to the right of the decimal are significant. So that's easy. So it's really the last one. So that 57.00, that last 0 is significant. So the one between that 0 and the 7 are significant. So that's 4 significant figures and 7 significant figures. Zeros at the end of a number, but to the left of the decimal, are significant if they have been measured or are the first estimated digit. Otherwise, they are not significant. In this book, they will be treated as not significant. Some books place a bar over a 0 at the end of a number to indicate that it is significant. This textbook will use scientific notation for these cases instead. There are a couple of rules that we will use. We have a bar over the 0. We can use that. And if you write in a decimal point like 50 and then put in the decimal point, that also makes it significant. So those zeros are not going to be significant. But if I put a written in decimal point at the end of there, that would be 4 significant figures. If I actually wrote it in, which is not usually done, so that would be unusual. So that would create 4 significant figures. But as that is read, there's only 4 significant figures. And as that is read here, as that is written, I should say, not as read, as that is written, it would be 4 significant figures. And as that is written, it would be 2 significant figures. But again, if I wrote in the decimal point, there would be 2. Or if I put a bar over one of those other zeros. Students may need to practice with examples in applying the rules shown in Table 4. Write each of the examples in sight of notation. Check the number of significant figures. So we're going to convert to scientific notation. That would be 5.03 times 10 to the 1. Notice the scientific notation only has 1 significant figure to the left of the decimal, and it's only going to have significant figures in it. So that would be 8.92 times 10 to the negative 1. Okay, so you're only using significant digits. So that would be 8 times 10 to the negative 4. Okay. So that would be 5.700 times 10 to the 1. Excellent. Excellent. Etc. 2 times 10 to the 6. And you would use all those because that's 0. 10 to the 0 is actually a base 10. That's legitimate. Okay? Excellent. The rules for determining how many significant figures are in a measurement that includes 0 are shown in Table 4. Significant figures in calculations require special rules. In calculations, the number of significant figures in your result depends on the number of significant figures in each measurement. For example, if someone reports that the height of a mountaintop, like that is shown in figure 12, is 1,710 meters, that's 3 significant figures, that implies that its actual height is between 1705 and 1715 meters. If another person builds a pile of rocks 0.2 meters high on the mountain, what would that would not suddenly make the mountain's new height known accurately enough to be measured as 1710.20 meters. The final reported height cannot be more precise than the least precise measurement used to find the answer. And in multiplying significant figures or dividing, your answer cannot be more accurate than the least accurate value. Therefore, the reported height should be rounded off to 1710 meters, even if the pile of rocks is included. Similar rules apply to multiplication. Suppose that you calculate the area of a room by multiplying its width by its length. If the room's dimensions are 4.6 meters by 6.7 meters, the product of these values would be 30.82 meters squared. However, the answer contains 4 significant figures, which implies that it is more precise than the measurements of the length and the width, because the room could be as small as 4.55 meters by 6.65 meters, or as large as 4.65 meters by 6.75 meters. The area of the room is known only to be between 30.26 square meters and 31.39 square meters. The area of the room can only have 2 significant figures because each measurement has only 2. So the area must be rounded off to 31 meters squared, because it's really more of a question of accuracy than it is precision. And the number of significant figures will indicate the accuracy, the overall accuracy of something. Here's a calculation. So you'll notice that there's 2 calculations here. One is addition, and that the 97.3 will hold it to 1 place value. So that would be the least precise value. So the least precise would be 97.3 would be plus or minus 0.1. And in the multiplication, you have 3 significant figures and then 3 significant figures. So even though it's going to be 658.05 as the answer when you multiply, you've got to have the answer as 658 because the answer has to be 3 significant figures. Table 5 summarizes the 2 basic rules for determining significant figures when you are performing calculations. Calculators do not pay attention to significant figures. When you use a calculator to analyze problems or measurements, you may be able to save time because the calculator can compute faster than you can. However, the calculator does not keep track of significant figures. Calculators often exaggerate the precision of your final results by returning answers with as many digits as the display can show. To reinforce the correct approach, the answers to the sample problem in this book will always show only the number of significant figures that the measurements justify. Providing answers with the correct number of significant figures often requires rounding the results of the calculation. Section Review. Which SI units would you use for the following measurements? A. The length of a swimming pool, the mass of the water in the pool, the time it takes a swimmer to swim a lap. So it would be meters, that's standard, that's SI, kilograms, even though in chemistry we'll use grams a lot, and seconds. And then express the following measurements as indicated. 2.20 milligrams in kilograms. And then we're gonna try a shortcut. So we have 10 to the negative 3 grams to milligrams, etc. Well, it could be thought of as being more like 10 to the 6th or 10 to the negative 6th, depending on which way you're going from milligrams to kilograms. So if you're going from milligrams to kilograms, it would be 10 to the 6 milligrams in a kilogram. So it would be 10 to the negative 6th is what you would get. So let's do some calculations. I'm going to skip problem 2. Perform these calculations following the rules for significant figures. The first one, you're going to round that to 2 significant figures because when multiplying or dividing, your answer must have the same number of significant figures as the measurement with the fewest number. So you're going to round that to 0.67. The next one, you're going to round to 2 significant figures. And that's going to be rounded to 14. And that'll be 2 significant figures. And the next one has to be rounded to hundredths place. Because remember, when adding or subtracting, your answer cannot have any more precision than the least precise value. So the least precise value is 0.45. So I need 2 decimal places there. Excellent. The next one. Critical thinking. The following students measure the density of a piece of lead 3 times. The density of lead is actually 11.34 grams per cubic centimeter. Consider all of the results. Which person's results were accurate, which were precise, which were both accurate and precise. So we have Rachel, Daniel, and Leah. Okay, let's see. Rachel was both accurate and precise. Daniel was precise only. And Leah was not accurate and not precise. Okay, the end. Have a great day and goodbye.